Today we have Mortaza talking about applied control theory.
Okay, thank you for introduction. That's a section we discussed about dynamic optimization. That was a little theoretical topic, but today I will try to review the control theory and I will go through the different setup of the control theory and some examples and simulations. It will be more practical. Again, this is an introduction. I hope that we have a sequence of the talk. After that, we talk about the applied control theory. We will go to the measures, the gain measures, and we will talk about the H infinity and setup of H infinity in control theory. So my talk will review. I present an introduction to this topic, and then I will discuss about different setups. My focus will be on feedback control and mostly the closed systems. And I will talk about the simulation, some simulation, both for the different setups, the open and closed loop. And I will discuss the first and second utility in the feedback control. And at the end of the story, we will talk about the limitation of the feedback control as well. So the control science is called the third revolution. Actually, after the Industrial Revolution, the control is an important topic, and I think that it has changed humankind life and our daily life. So its influence is incredible in everywhere, and engineering activities in daily life, and its contribution is enormous. Okay, so, and you know that the control plays a critical role in transportation, like all buses that you see in the street, all of them are controlled by the control system. Even the bus, the stopping and stopping in a stop is controlled by that. And also the aerospace is dominated by the control. So in industrial equipments as well, you know, any assembly line, any production line is robotic, and they use the control and control system. Also, in the daily machines that we use, we see that even washer, dryer, coffee makers, all of them use the control systems. So in a space system, any rocket, satellite that you see, these are using this science, and also in advanced products like the AI that you are using these days to solve some problems, or you get the consultation on anything, so it uses the control as well. Okay, so, and at the end of the story, in automation field like agriculture, medicine, and warehousing, anywhere you can find a footprint of the control science. So what is a control system? A control system is defined by its components. And below of this picture, you see a control system and its abstraction. I will explain the component and I will explain the abstraction. And later on, we will talk about the methodological aspect that is more mathematical. So a control system components are a controller, actuator, and process. So we target a goal, for example, to control the speed or the distance or anything. And so we have an input to the controller, which is our prior knowledge, or in closed system, we have feedback as well. We will talk later. So the controller sends the signals to the actuator, and the actuator will process that and then force the process. So the process is something that happens in physically that we see. For example, here is a simple example. As you see, we have controller is electric circuit. So this controller send the voltage to the motor, and the motor torque is the circulation of the motor torque by the shaft will be transmitted to the disc to rotate this. So the process is here. The disc rotation is our process. So the motor is our actuator. So if we wanted to explain, the controller must generate the signals and commands to the actuator. In any system like that you are working, actually you have the controller that generates the commands to the actuator, and then the commands aims to achieve an expected process output, like the speed or the movement of the muscles, or controlling the movement in the Parkinson, for example.
After the defense firms,
Exactly.
the actuator is taller.
Yeah.
And the output is the EMG express.
Great. So the process here is rotating movement of the disc load, and the controller, as we explained, that is the electric circuit that generates the control commands, and actuator is the motor that we apply the torque of the motor to rotate the disc, and objective is to regulate the disc speed, okay, to a desired level. Actually, everything is done to control the speed of the disc, okay? So this is a simple demonstration of the control system, okay? So we have two main category or two wide range of the control system. One is called open loop control system, and the other that later I will talk is closed loop. What is the difference between open loop and closed loop? In an open loop, we use our prior knowledge to set the controller, okay, without any feedback from the performance of the system. So actually, in a system that is open, the system based on the prior knowledge and does not use any feedback. This is the main difference, okay? Other aspects are, moderate change that in any case can be happen, but generally in an open we do not have any feedback. Here you see the previous one was an open system or open control system that I presented. So here is again is a heating. For example, this is a dryer. As you know that in a dryer machine you set the time and temperature, okay, and then everything will be here, okay, in the controller, and it will send a command to the heating elements, and then the clothes will be dried in a certain time, okay? So if something happened here, there will be no feedback to get back to the controller and change the commands, okay? So sometimes you see that after, when you use the dryer, your clothes are not completely dry, because because of the performance deviation, or there are some external shocks, or any disturbance in the process that can happen. So as I mentioned, the open loop control system depends on proper and accurate knowledge that we use to set the controller. Any inefficiency, inadequacy in the knowledge will cause that the performance will be deviated from the targeted or the goal of the system. So the performance of open loop control system heavily depends on the quality of prior knowledge, okay? So, and good prior knowledge can result in the good performance of the system, and increase the likelihood of the achieving to desired output. But you know, if the knowledge is poor and unstable, then it will cause inconsistent or incorrect outcomes. So generally, because of these two features, that it uses a barrier or the knowledge, then any restriction in that will be called as a backward or drop back of this system. So lack of a high quality prior knowledge is the main challenge in the open loop system. The other one, which is also important but is not as important, the first one, is the environmental change that can affect the performance of the system. As I mentioned, that the condition maybe changes, or the load on the system may be changed. Anything can happen that externally is out of control. So in open loop control, we cannot correct it. Okay. The other system is closed loop, or sometimes we call it feedback control system, shortly. So this one not only use prior knowledge, but also it use the feedback from the system. Okay, so both of them are used. It means that the controller will combine the prior knowledge with the feedback that it receives from the system. So to have a feedback, we need some additional, compartment in our system. In closed loop control system, we have two compartments. One is the sensors, and the other one is estimator. The sensors, in fact, measures the performance. For example, if goal is to set the speed of the disk rotation, okay, so the sensor measures the speed, okay. So sometimes we need to an extra part, which is estimator, to process this collected information or collected data, to convert them into commands can be used or can be used in the controller to combine with the initial or prior knowledge, and then send the command to actuator. So these two parts, sensor and estimator, in fact, are two main parts in the feedback loop, okay? So sometimes we combine them. We have just sensor. Sometimes we have sensor and estimator. Depends on the data that are collected by sensors and the complexity of the system. So how is this mechanism, the feedback mechanism in closed? Actually, the sensors measures the performance. As I said, that the process output is the performance, and then sends this data collected to the estimators, and the estimator will refine and, in fact, digest the information and pack it and formulate it to send to the controller, and controller use the feedback and prior knowledge to send again to revise the command to actuator. So if the sensor is reliable and accurate, we can ignore or delete the estimator. We do not need to estimator in some system, but often we have both of them together, okay? So in a closed loop system, it will be more reliable than open loop, okay? Because any disturbance, shock or disturbance deviation can be corrected by using this, actually the feedback mechanism. So it is much better than, theoretically much better than the open loop. So as I mentioned, we have two types of the closed loop feedback control system. One of them, as you see, we have this controller actuator process, and for the feedback we have sensor and estimator. Sensor collect the data, or measures the performance of the output and deviation, and then sent to the estimator. Estimator compiles the data and sent to the controller. Controller use the prior information and the feedback, and then again send the command, and this loop will happen to maximize the output performance. So sometimes sensors are accurate enough and we can ignore the estimator. This system just have the sensor, but there is no estimator in the second one. But however, both of them are close. So as I mentioned in the beginning of my talk, the most important part of the control system is the methodology. And this is that you mathematicians do. You mathematicians formulate everything mathematically, everything that is happening in the world. So you formulate it mathematically to predict, to explain, okay? So in fact, the methodology means how can we abstract the performance of the system from the scratch to the end, okay? And then make the performance better, okay, using the mathematical formulation. So we abstract this system mathematically. We call it abstract the mathematical essence. So here in the bottom of this figure, you see this is an engineering system, that it is happening in the reality, okay? So, but on the top here, or much better, I can say in the middle, you see the abstract methodology or the mathematical representation of the system. For any part, you will see corresponding part that which is mathematically represented, okay? So, for example, here, as you see in this system, we have the controller. The controller here shows that because the system is a closed loop system, okay, or closed loop control system, the voltage that will be sent to actuator is a function of expected velocity and also the performance or the feedback velocity that is measured by the sensor here, okay? So the controller will formulate that, okay, and set the voltage and send the voltage to the actuator. So here the actuator is the motor torque, okay? So, and this motor torque will be transmitted to this to rotate the disc. So actuator here converts the voltage that's received by the controller into the torque or the rotation of the motor. How? You know, this is the physics you have studied in secondary school. You are familiar. The voltage is Ri basically if there is no inductance. So you know that this part is because there is armature, and because of the armature we have the circuit in the system as well. So the total voltage is equal to Ri. R is resistance and I is the current in system, okay? So, and then the I will be set here, because if it receives a level of voltage that is set by the controller, then based on these are given, the R and L are given, and this one is actually the endogenously generated circuit by the armature. So then totally we will see how much will be the current in the system. The current sets the torque of the motor, okay? So the torque of motor is here mapped, actually here, both of them are, we can say sometimes we set the current by this function and then send to this one, and here the torque will be determined, how much will be the rotation of the motor, and then it will be transmitted to this, okay? So, and then this is the torque that will be sent to the process. The process means the rotation of the disc. The rotation of the disc depends, this is a function that you know, this is the transmission, the rotation by the motor shaft, and this is the velocity of the disk. So the velocity of the disk depends on too many factors. This is actually, the inertia and this viscous. So both of them determine how will be the speed. So the speed is the control variable that will be set at the end. So then again, we will have the performance which is the speed of the rotation of the disk, and it will be measured by sensor and send the feedback to the controller. If the speed is far from the, actually the targeted one, or it will be more or less, then the sensor will measure this deviation, okay? And if we have estimator, we'll convert it into how much should be combined as a proportional to the initial or expected velocity. Then again, it will send the voltage to the actuator or to the motor, and it will continue to reach the target. I will show you by the example here, the simulation that we have. So actually, mathematical essence that we talk is all formulation that you mathematicians do mathematically to represent this engineering system. And you use the mathematical techniques and knowledge to analyze the control phenomena, what is happening here, and how can set the objective based on the control principle and how to design the control method to guarantee the performance of the system. So here in this slide, I explain those, as you see in that figure. I explained the controller input. The controller input is prior knowledge that we have, expected speed that we wanted to set. V is expected speed, and also the feedback speed that comes from the sensor. So the controller output is the voltage, okay, or the command by the sensor. Controller is the voltage that will send to the motor. And here, the mathematical essence means all mappings that you have. For example, here mapping of these two to voltage, okay, and also then you have the other mappings. So this is simple for you to explain it. So the main question that we have in control method mathematically, we need to why certain control phenomena occurs. It means that why this procedure that you should know and you should know to explain that what happens in the armature that it rotates, okay? So the armature, that's electrical engineering knowledge. So you should convert it into the mathematical knowledge, okay, and representation. How to analyze it mathematically, as I explained. So how to design the control method with guaranteed properties. This is that we set the comments by the controller. How to replace the empirical tuning with objective principle, as we see that the measure by the sensor and the secondary type of knowledge is sent to the controller. Okay, in summary, to explain the role of the control theory, the control theory focuses on mathematical essence of the control system. Okay, so and provides understanding the system behavior, predicts the outcome of different control methods, and design controls with guaranteed performance. These are the core essence of the mathematical essence of the control theory, and then bridge the gap between the engineering implementation and theoretical principle. So hand-on experience mathematicians work with the engineers, okay? So here I get back to the actually open loop. I will explain this, mathematical methodology in the control system, and I will explain more in detail, and I will simulate some examples. So let's start with a simple open loop control system. Then this is a practical example. So as you know, we have this compartment, the control, actuator, and the process. All of them are mathematically represented, as I explained. So the goal is to set the performance is the speed of the disk as much as close as to the expected velocity. Okay, so here we have the rotating this speed, which will be controlled. Okay, and so we have different compartments as I explained. So let's get back to mathematical representation. The process that we had, this is the two main equations that we had. If we combine them, okay, we will have this first order differential equation that this is clear for you. And as I explained that the J is the inertia of the rotating disk, and B is the viscous friction coefficient. And then this is the torque of the motor, that then what will be set, the result will be V, or the velocity of the disk, okay, by solving that. So this is a simplified system here that we have. So then the velocity of this will be set, and given the torque of the motor, you know that here there was the voltage set by the controller sent to the motor. Okay, the motor voltage set the current. Okay, the current will be set as you know, I take it as exogenous in the last equation, which is the torque of the motor is the constant times of the times of the actually current. Okay, so given that we have the constant torque at T0, the system has the expected velocity of the, actually, this is the response velocity of the disk that you can solve the system. So here, as you see, this coefficient is so important for us. The tau is JB. You know, when we have large inertia, the response will be slower. So you know that when the disk is big and the initial inertia is high, so the response will be slow, and the disk will start to rotate slowly. Okay, so then this friction as well, the viscous frictions shows that if it is high, then the convergence will be okay faster. Okay, so again, we mentioned to the limitation of the open control system. I do not repeat them. As you know, here we have physical parameters that we need these parameters. If we have any accurate, as much as our knowledge is accurate, then the performance of the system will be better. Okay, we will reach to the expected performance. But if our prior knowledge about this inertia and also the viscous friction is inaccurate, okay, then the performance will be far from the expected performance. Okay, and also there will be some external disturbance, and this model inaccuracy means that the mathematical representation that we showed, that for example the constant for the torque of the motor was T equal to TMI. Okay, that equation shows that how much is the torque of motor. This constant is important as well. So we had this T is equal Tm is called the constant of the torque, and I is set by the equation that we had. Okay, so this I set by the voltage sent from the controller to the motor, and we show that here you had LD I dt plus Ri should be equal to V. So here the I will be determined. Okay, so and I will be sent here, and the torque of the motor will be this representation. This constant, also this measurement of any of them, means that the model inaccuracy may happen if we are not accurate. Okay, so and without feedback, the system cannot reject the disturbances or actual to compensate any uncertainty that it will be in the system. Okay, so here I have written the second part is actuator dynamics. This is the actuator dynamics, what will happen in the motor, okay, in our example. And then we combine them, okay? Here you know that by this, the R is the resistance. I explained before what is R is resistance, I is the current, and L is armature inductance, okay? This is called the internal current that is generated by the inductance, okay? Sometimes we can say, okay, it is ignorable and we can ignore it. I will show you that we will simplify that. And Tm, as I explained, is a constant for the motor torques. It means that the current will be converted or mapped into the torque by this constant, okay? So here is the combined first order actuator model. The previous one was the actually, here we have some parameters. The parameters here, for example, the inertia, the initial inertia is 10 Newton meter square of the seconds per round. This is the inertia, initial inertia. And this is the viscous friction, which is 5 Newton meter second per round. Okay, that is the friction. And R is measured by ohm, you know that from physics. So L is inductance, also measured based on the H, because you know that this is armature, and armature is what is, I don't know if have you seen the armature, for example, in a motor, you have this is, and here you have, for example, four, these are the inductance. So these are connected to each other, and we have two. For example, in one phase, we have this is the voltage that comes, and then it will rotate because of this field, electrical field that is generated by this the circuit of the that the current in this. Okay, so and also sometimes it happens that we have, because of this inductance, we have the currents generated by the armature. So here we have this in parameters, and we will use these parameters to simulate a system based on the equation that we had, okay? So sometimes we can, as I mentioned, if you simplify the model, you will see that L divided by R is far from the J to B, and we can ignore it. It's ignorable, and then our system will be simplified like this one. So here, you know that we have a bijective mapping between the voltage that comes from the controller to the torque. So this is constant, this is given, resistance is given. So when the controller set the voltage based on expected velocity, and also based on the feedback that later will modify that. So the voltage will be set, it will be sent to the actuator. In our case, the actuator is the motor. And then this is the motor torque, or the rotation of the motor, okay, shaft. So this is a bijective. And why I call it bijective? Because it depends which one is given, okay? Later on, then we can set the voltage based on the feedback that we will receive. I will show you how can we modify that. So this is what happened in the actuator block, okay? So given that we have such a unified controller actuator, okay? So here, I mean that what is the bijective? Because this means that unified mapping, the motor torque is defined by the voltage, because the other are constant, okay? So this is simple mapping. So if we have the expected voltage is defined, then the voltage is so sorry, it is velocity, sorry. The expected velocity is given or set before based on our knowledge, then this will be sent to the actuator, okay? So here we have a function of the expected velocity, and easily you can convert that. Sometimes you have the feedback, okay? So, and also you have f of expected velocity is defined, then the torque is defined like this one, okay? So here we have two functions, f capital and f small, depending on the information that we have. So the actuator can be represented by this unified control. So here we have this simplified one, as you see here. I represented mathematically, and this is the process. This is the speed of the torque. That the torque comes from the motor, and then it sets the speed of the disc, or the velocity of the disc will be determined by this process. So this is open because we have no feedback here in this open loop, okay? So, and let's go to this simulation. So suppose that the expected speed is 1, okay? 1 means that the speed is 1 round per meter, okay? Or 1 round per second, or, and you can set it 100, 180, okay? So actually in the electromotors, in reality, we have 1,400 rounds per minute, and also we have 3,000 rounds per minute. These are two types of the speed of the motors that we have, or the motor torque. Then it will be converted to the speed of the disc, okay? So here we assume that J and B are given from the table that I show you, and this is the mapping that we have. Okay, this is a simplified mapping. So let's go for the simulation, and then we will use the MATLAB code. I use the MATLAB for T is equal to 1. This is the torque of the motor, and I assume that it is constant at 1. So what does it show? You know, the horizontal is the time, and the vertical is rotation of the disk. So here, our expected speed or velocity was 1, okay? So then we set t is equal to 1 as well. Then if t is equal to 1, here we set t equal to 1. So this one is constant, Tm is constant. Velocity in the disk will be determined by I, which is set here. Okay, if you set t equals to 1, you will have I, because this is constant. Okay, so the I determines the velocity or the speed of the disk. Okay, so here we set t equal to 1, and this is the performance of the system. As you see, when t is equal to 1, in 10 minutes, the speed or the rotation of the disk starts to rotate, and it will reach to 0.2, for example, round per second. Okay, so, and it will converge, so it will be constant in 10 seconds. But as you remember, our targeted speed was 1, or expected speed was 1. So it is far from 1. Okay, so we have no feedback to control. So in 10 minutes, then the speed of this disk will reach to 0.2, okay, round per second, and it will be constant over time, okay, forever. This is the result. So what will happen? This one, even the time goes to the infinity, as you see here, when time goes to the infinity, although our expected speed is 1, but the speed or the rotation of the disk will be 0.2. So let's simulate another one. We set t is equal to 2, okay? And then we will observe that the performance of the system is that it starts from 0, the rotation of this starts from 0, and reach to 0.4 after 10 minutes. Okay? After 10 minutes, it will reach to this point. So now, as you see, again, the performance is much below the expected speed that we expected. Okay? Is it clear? Okay, I hope. So no, because it is a engineering problem. I'm so sorry that I example the engineering. So the velocity of the disk will be 0.4 even when times go to infinity. Okay, so it will be constant over time. Okay, so but as you see here, it's smoothly it will take to reach to this point, and this is the maximum speed when t is equal to 2. So what is the optimum? How can we reach to, how can we set, here we use some information. For example, B, J, initial inertia, these were that were given, okay? And we set the voltage, and then the voltage was sent to the actuator or the motor, and the motor torque was sent to the disk, and this is the performance of the disk. Okay, so but we see that it is far from the expected speed. So what shall we do? So as you know that in both cases, we have the performance is 0.2 or 0.4. So what is the optimum? We can find that if we wanted to have the expected speed is in infinity should be equal to 1. Okay, this is the expected that we expect in at the end of the story we have a speed equal to 1. Then we can choose t such that 1 over t should be equal to this one, and then t should be equal to 5. Okay, so this is called proportional to constant torque. So the steady state is proportional to constant because we saw that if we set t equals to 1, the performance or the speed of this will be 0.2, and when we set t equals to 2, we saw that the time infinity, the performance will be the speed equals to 0.4. Then from that we can find this approximation that it is proportional the velocity of the disk when times goes to infinity with respect to t, the torque, okay, is 0.2. Okay, from this we can find that when we set this one equal to 1, we will get the t equal to 5. Now I simulated the model when t is equal to 5. So I set t is equal to 5. So this is my initial knowledge or prior knowledge, and parameters are part of my prior knowledge. Then I set the system, okay, and simulated. So this is the performance of the disk or the speed of the disk over time. As you see, after 10 minutes, the speed will reach to 1, which is my expected. Why? Because I set the torque equal to 5. So if I set this one equal to 5 and this constant, then the I will be determined, okay? And I will be, set the torque, okay? So then the velocity of the actually the disk depends on t, okay? If t is equal to 5, this is the optimal level. So I should set voltage such that I have t equal to 5. Based on this equation, given that I don't have this one, I have the resistance. What voltage I need to set I such that t is equal to 5 given Tm, okay? So this is set by controller. So this needs my information. I simulated for t equal to 1, t equal to 2, but my performance was much lower than expected speed. So I revised it. Okay, so I revised it, and then I got this, given this constant, the t should be equal to 5. And if I set t equals to 5, my expected, that the differential equation that I showed you and I solved for the velocity, okay, then will determine when I will reach to this point. Okay, it's clear. It's a simple differential equation for, the undergrad course.
So T equals 5 should be an output of the console, right?
Yeah, this is optimal. Okay, so t equals to 5 actually here shows that how much should be I, and I determines how much should be U set by the controller and sent to the motor. Okay, then for that one, we see that based on this equation, let me get back to actuator and torque, here. So here, that T0, if it is 1, we have this parameter. We have J, inertia was, and B was given. So based on this, after 10 minutes, we will get to 0.2 if T is equal to 1. And if T is equal to 2, then after 10 minutes, it will get to 0.4. And if T is equal to 5, after 10 minutes, we'll get to 1, okay? The expected velocity. So you know that from here, what voltage do we need? What voltage do we need depends on T that we set constant, okay? And when we know this is Tm is constant, this map is given that it is actually when you have the current, it will map current to the torque of the motor, the circulation of the motor. So this is the constant, for example. So we want to be 1, for example. We have this constant. What current should we have? Current determines that if you ignore this one, inductance, okay, then Ri should be equal to U. R is the resistance of the, armature. And you know that I is derived from this equation, then what voltage should be sent, okay? So this is from our prior knowledge that the controller set the U determines I determines the torque goes to this equation, torque goes here, and then the velocity of this will be determined over time, okay? So, and we simulated for different value of T based on our assumption, and we solved for that, and mathematically we concluded that T should be equal to 5. Then, in that case, the speed of the disk will be equal to expected speed of. So, yeah, this is the final result that T is equal 5 is valid open loop control input, okay? So in that case, we will have that the speed of this will reach to expected speed after 10 minutes. So is it enough? Maybe you conclude that it is okay. By multiple simulation, we can find the optimal solution, okay? Or by any other mathematical, solution, maybe we can find the optimal T, okay, T naught. Somero has worked on the initial value T naught. Okay, so you may find that initial value of T and say, okay, if you set T is equal to 5, for example, in this case, based on this prior information or knowledge, then the disk will rotate by 1 meter or 1 round per second in 10 minutes. And that is okay. In 10 minutes, we will reach to the optimal speed or expected speed. But who knows? Is there any other factors that affect our result or not? Some externality or loads on the disk or anything can change the result, okay? So how about the parameters? The parameter uncertainty is a critical challenge that we discussed. External disturbance, overload on the disk, these are, and model error, maybe the model has error, okay? So how can we control that? So we need the feedback control. So let's go to the feedback control. These are the motivation for the feedback control. This is the conclusion. We have some variation in these factors. the low torque, friction, external disturbance, actuator imperfections, and then the key issue is that if desired state change or if the disk experience unexpected load variation, an open loop control alone is insufficient. So we should have a closed loop. So let's go to the closed loop and find the feedback control. So the feedback control theory has two approaches. The first, utility. So from this simulation, maybe someone be confused and believe that the open loop is good, but we concluded that it's not, because the reality shows that the real world system always contain uncertainty. So the first utility in closed loop considers the uncertainty in reality. So what does it mean? As you remember, in my system, I had no external shocks or uncertainty. I can insert that uncertainty and see how can I use the feedback control to control for that uncertainty. So here is an example. I will get back to previous slide because that was explanation for, motivation of this considering uncertainty. What is the difference between this system and the previous one? Can you tell me? As you see, the previous one, we had controller, okay? And here we had the process. Here, as you see, actuator is combined into controller. Doesn't matter, okay? Because we simplified our system. The most important is that here we have the disturbance. The torque disturbance is an input to the system, okay? So then the process or the performance of the system is affected by TD, which is something that is external. This is a disturbance. For simplicity, I assume that it is a uniform distribution, okay? You can assume any distribution based on experience. In any case, for example, in your case, you were talking about the external shocks, so you can assume that it is random or any other distribution. Okay, here I will assume. So I will assume that it is uniform distribution. So the rotating this is speed control with unknown torque disturbance. So here in the actuator, I assume that there is the torque disturbance and it will affect the right-hand side of the process equation. Then it will affect the speed. Okay? So how can I control for that? So the effective torque will be T, the torque of the actuator, minus this one, because it is a negatively affect my system. Okay? So then if T is perfectly chosen in open loop control, so again, we can control. So we can assume that we have this one, okay? And we assume that this T is perfectly determined. For example, like the previous one. Again, this disturbance in open loop will affect our result, okay? And it will cause that the steady state speed away from the desired value. Okay? So now I will use the simulation under uncertainty. Okay? So I will use all information that I had. The J was the inertia, B was the viscosity friction, all of them the same, but I will insert the TD, which I will assume it is not equal to 0, and I will assume the uniform distribution for that. So TD, I assume that TD is distributed, for example, uniformly between minus A and A. Okay? So then the dynamics of the system will be this one. Okay? So this is the same equation that I had for the process. I added this one to the right-hand side. The others are the same. Is it clear for you? Right. So what will happen? So if we have TD we can assume that it is randomly distributed or anything, but here I assume that it is actually uniformly distributed. And let me go to the observation and I will get back to explain what happened. So this is my MATLAB simulation under alternative assumptions. So when you have the external distribution, so it is random, okay? So you cannot control what. So it depends how many simulation do you have. So this one is the same as before for t equal to 1, okay? Again, I will assume t is equal to 1, but I inserted one more part is td, which is the external input into the torque. So, and it is randomly distributed or uniformly distributed here. I assume that, and then I simulated for different simulation. These are two alternative simulation. As you see in any simulation, the time is the set 10. Here, in the first simulation, with the same distribution assumption, after a while, after almost 2 minutes, I will close to the expected. But in the next simulation, because it is random, as you know, after 2 minutes, I will get to 0.6 and it will be a steady state. Okay? So this is how can I control? How can I reach to 1? Okay? And when I can reach to the 1, this is my expected. When there was no uncertainty, I could find t is equal to 5, and I control for that. But in terms of the uncertainty, the results will be different. Okay? So even if we know the torque of the actuator for the deterministic case that there is no uncertainty, the existence of this uncertainty will affect the performance of the system. Okay, so now I will control for any feedback. I will use the feedback. If we have the torque disturbance, okay, which is unknown, and we have some prior information about the system performance, I will use the control law of the T. So my question will be, how can we design a control method that suspects, okay, the torque disturbance regardless of its concrete value, okay, the concrete value. For this purpose, we resort to the feedback control. How can we do that? If we set a sensor in the system, okay, and the sensor measures the performance, then the velocity of the disk, this is the real or the actual velocity, and this is the expected, and the deviation could be positive or negative. Okay, in our simulation, it was, expected was 1, but the performance was much lower than the expected. But maybe in another simulation, we reach to the point that is over than 1. So this could be, again, negative or positive. So if E is positive, then the T could be set to the T of max that we set already, for example. If E is equal or less than 0, then it can set to minus T of max to control for that, okay? So in this case, we have a feedback control law that we insert in our model, and then we can reach to or optimize our system performance, okay? So here, as you see, this is the process that we had. This is the performance. And here we have the torque disturbance. So in controller, before that, we had just this one, okay? But now we inserted this law of modification or the law of feedback. Then T will be T max or minus T max, depending on the speed is below or above the expected speed. And how can we set this one? By this control loop, okay? So here we have, yes. Yeah.
I missed something here. So I just want to know that what is this negative feedback?
Exactly. You know, here you have this is T is equal to when you have no external, okay? So before that, you had U set by the controller sent to the motor, and T was determined. T was the right hand side of this equation, and the speed was set. And we find that T equal to 5 was the optimum, okay? So now the question is that if we have TD, this is the external shocks to the torque, so this will not be T naught that we had before, okay? So the solution will be different, okay? So yeah, this is the T max is T5 that we had. Yeah, the optimal that we had, yeah, is minus of the. Yeah, it's the rule of controller, that's what? No, it is negative because it goes to correct for that. If the speed is much higher, okay, so here, you know, the speed is determined by the T naught, okay? So this one, we should set this one to a level. So the T max means that we had T5 for the optimal when it was 0, but now it is not equal to 0. So we will observe the speed. The speed may be 0.6 or 0.8 or maybe 1.2, okay? So here I showed in this simulation. Oh, sorry.
England.
Yeah,
These are your bombs. T max.
yeah, exactly. Yeah, exactly. Depending on the distribution that I assume for the uniform distribution of T. Because I assume that minus A and A for the distribution, okay, I will show you graphically. So here, you know, the performance of the speed is, for example, in one simulation, we reach to 0.6. In one simulation, we reach to this point, and maybe in another simulation, we reach to this point, okay? It means that the speed will be much higher than expected or is lower, okay? What will happen if it is lower? No, the speed is V expected, okay? And this is V expected, okay, minus V, okay? So this is the V that we measure, actual velocity, okay? And this is expected, we set it equal to 1. So here, for example, in one case is 0.6, one case is 0.8, maybe in another is 1.8, okay? Because of what? Because of TD, which is external. Why? Because in this equation that we solved here, that we had the velocity was this is the change, and we will solve for this one depends on T minus TD, okay, as well, okay? So this determines what will be the velocity over time with the solution for this, okay? So in the first case, when you have TD and it is actually the randomized variable, so it will reach after 2 minutes to this steady state, but the speed is 0.8, almost 0.8, and here is 0.6 after 2 minutes.
That's empty. So I'm trying to connect it with my word.
You know, without any disturbance, okay, our T was optimum was 5. And we show that in open loop system, after 10 minutes, we reach to the optimum, okay? So 5, optimum, T optimum, okay? It was 5. But now we have an external shocks, okay? So the external shock will affect this velocity. This is the velocity, you know? This is the velocity of the disk. But the velocity of this will change to reach to this plateau here after 2 minutes. Here after 2 minutes will reach to this point. But maybe it becomes here and then goes to the another point, okay? So because it is a random variable, okay, it will affect the performance of the system.
So your model allow it to go upward.
No. We wanted to control that. What happened? Yeah, we define this rule of the control to see if the speed is much higher. Okay, here we expected is higher than, this means that the speed is much lower than the expected, then it will set t is equal to t max. Yeah, and if it is not, if it is negative, it will set the t is equal minus t max. Yeah, here is, just let me show you the,
if E is small, for example, like you observe the we also can be 1.0, and then you also set T to be -5. Is it too much?
yeah, exactly. Because of that, this rule is not effective, and we will define another rule. Okay, it's proportional. I will show you that, PID. So to set the t at the maximum or the minus max, okay, to control for those disturbance, the switching between these two alternatives will affect the performance, okay, and it will be dynamic up to the point that we will reach to the t is equal, v is equal to expected, v will be equal to 1, okay. So
Choose a knowledge.
actually, we assume that there is no uncertainty and we solve that. But I find it by simulation, but you can find it mathematically. Yeah, yeah, yeah. Depends on the parameters that we have. No, 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 no. That was not initial guess. Actually, I observed that, the V, when I solved for V or the performance of the disk, okay, what was important there? T naught was important, okay? You can find that when T goes to infinity, what is the optimum level of that? And I showed that. In my case, when I set T is equal to 1, okay, the speed was 0.2. Okay, when I set the t is equal to 2, a speed was 0.4. And from that, I showed that v infinity should be equal to 1. So because of those performance simulation I got, maybe you can solve it mathematically, okay? So by simulation, I got that there is a proportional relation between t, okay? So, and then I show that it is equal to, like 2. So then I said that, okay, V infinity should be equal to 1. And what should be the value of t? It is equal to 0.2. Do you remember? So V infinity, in my case, with respect to 2, I figured that it is 0 to 0.2, okay? So because I observed that V infinity, when I set t is equal to 1, okay, then it was 0.2, and if I set t is equal to 2, I got that V infinity was equal to 0.4. So from here, I figured that the V infinity with respect to t value that I set is equal to 0.2, okay? So from these two equations, you will get that, from this, you will get that V infinity with respect to t is equal to 0.2, okay? From observation, that simulation result that I had. So from this, I got that if I wanted to V infinity be equal to 1, which is equal to V expected, then 1 over t is equal to 0 to 0.5, then t should be equal to 5. I derived that by simulation, okay? So, but you can set it mathematically. How? This is the performance of your system. Yeah, this is my simulation result. So let me show you. Actually, this is the solution to first order differential equation that we had. Okay? So what is T naught optimal level? So it is a vector field, okay? So you wanna to V when T goes to infinity, V goes to 1, okay? So you can find the solution for this vector field when and what value of t, okay, guarantee that your v will be equal to 1 when times go to infinity. Okay? From this solution of first order differential equation. Got it? So, and that depends on these parameters. And given these parameters, t was equal to 5, okay? The optimum that I obtained by the simulation. I think that you got tired. Yeah, I talked too much. How much time do you have? I exceeded my time. I passed. Okay, so, okay, just let me show you this result because I think that it is important to know how this actually feedback law will work. So we set this feedback law. Simply, we assume that when the speed is below the expected, then t will be set to t max, and when the speed is above the expected, then t is equal to minus t max. This is the rule that we can set, okay? This is a rule, okay? So you can use another rule. As well as I hear this one is another rule, okay? This is proportional rule. This is called proportional feedback control. Okay, so but before that, let me show you the result. So this will be my controller. We'll set the t, and the t, when you have t set it depending on this value or the performance that comes from the sensor to the controller, then you will see that the process will set, okay, the t will be t max or minus t max if the speed is below or above the expected speed. Okay, so then this will help us. This is extreme feedback with uniform distribution. If you have such a uniform, okay, the sensor will measure the speed, will send to the controller, okay? The controller will use the rules that we set, and comparing with the expected, velocity, we set the t max, okay, or minus t max, and then you see that after below 1 second, it will reach to this point, and this is the plateau. So the speed will be at the expected. So with help of this, we got, this is called the first utility of the closed feedback control. Okay, so, but this rule does not work always because you always switch between the maximum and the min of max. Okay, so it's not, in reality, in some cases this is not good. Okay, so you need some more flexible. Here is the proportional feedback control that is more flexible. I think that I can leave this for next session if you wanted to have a break. And then Xuan is extremely tired. Sorry? Yeah. I have too much slides, and I have more slides. I can talk over the semester. Yeah, I hope that you be interested in these topics. Okay. Sorry, I dropped you to the undergrad program. It's not pure math, it's reality engineering and also the math.
You're absolutely never left the thing. So this.
Okay. Okay, let's have this proportional for next time. I can. Yes.
You have a presentation next week there at Leon.
Leon will be on Wednesday. Yeah. Okay, thank you for listening. Thank you.